Hello, for this week we will go again the kinetics of a particle and the last subject, which is impulse and momentum. This week we are gonna go concentrate on impulse, then we will jump to the momentum later on. Let's go through the principle of linear impulse and momentum. Using kinematics of the equation of motion, we know that the total force is equal to the object's or the particle's mass multiplied by the acceleration, which we know that acceleration is the rate of change of velocity with respect to time, which is m dv dt. We know that from we need to define that at t is equal to when time is equal to the first time, or whatever you call, you can assign it v1, and t is equal to t2, v is equal to v2. Let's say the initial time when t is equal to 0, velocity can be at rest, which is 0. Then the t is equal to any time, you can make it a final velocity. And if you take this dt into the left side, is gonna be total force multiplied by dt is equal to m dv, which we take the both sides integral, because we know that at t1 is v1 and t2 and v2, so we can take the boundary of this integral, and we can end up these equations if we take the velocity velocity integral, because we know that the mass is constant, it's not changed by velocity. So it's going to be v2 minus v1, mv2 minus mv1 is equal to total force and time, the time integral from time 1 to time 2. This equation is called principle of linear impulse and momentum. From the derivation, it can be seen that it's simply a time iteration of the equation of motion, which is here f. If you take the derivation with respect to time, the integral with respect to time, it's gonna be f and dt. It provides a direct means of obtaining the particle's final velocity v2 here after a specified time period when the particle initial velocity is known, which is v1, and the force action on the particle are either constant or can be expressed as function of time. So if it is constant, so we know that is delta t, which is we can say f delta t, which if the force is constant, which is applied, is gonna be m v2 minus v1. But if it is a function of time, so we need to take the integral. Then after that we can apply this equation. If we concentrate on linear momentum, it is represented by capital L is equal to the mass of the particle multiplied by the velocity. Both of them is a vector of quantity, velocity and in linear momentum. M is the mass, is a scalar. Linear momentum vector has the same direction as the velocity vector, and its magnitude is m multiplied by the velocity, which is kilogram meter per second. And for the linear impulse, which is shown by capital I, is equal to the integral of f dt. So as you remember from the previous slide, we defined on the left side is f dt, and the right side is the, here let's say f dt, and then here is the m dv. Here is the linear momentum, and here is the linear impulse. Let's go back to our original slide, which is here, and here is the vector quantity, which means, again, here is a vector quantity which measures the effect of a force during the time, the force x, as we know that if force is the constant, so f delta t is gonna be our impulse. linear impulse. It is a scalar impulse x in the same direction as the force, which is F multiplied by T, and which is Newton multiplied by the second. Newton second is the impulse quantity. So when you take these guys, it's gonna be the same thing again, because we know that kilogram meter per second square is Newton, so it's gonna be the same because it's gonna be equal, right? If it make it with a graphical representation as f, if f is with change by the time as it is like curvy, so you need to take the integral from this period to this period. But if f is constant, you just need to multiply with the delta t, because we know that the curve under it is gonna give us this area is gonna give us linear impulse. So it's hard to calculate it, this kind of shapes. So we take the integral in order to find the area of it below. But if we know that is constant, it's a rectangular, just multiply and then we are gonna get the under area shape. Let's keep up the principle of linear impulse and momentum. We know that this equation, which is modified from the previous one, which is here, right? This is a minus, so we take in the left hand side, and we end up m, the mass of the object multiplied by the velocity, the first velocity, initial velocity, plus the impulse term, right? Linear impulse term is equal to the mass multiplied by the final velocity of this object. As we see from the diagram, if we have a particle and then if it has a momentum, a first momentum, which has direction on the right hand side, right and upside, and if you see the second one, if we hit with an object or whatever it is, like impulse in the below side, right, in below direction, downward direction, so it end up the velocity change, the momentum change of this particle in the almost horizontal on the right hand side. Due to the like this diagram, we see like what is the effect of this momentum and impulse gathering and the final momentum diagram. We can divide it into the in x direction and y direction and z direction, because it's a vector quantity and then we cannot mix up, because if velocity in I direction, just we need to represent the I direction force, I direction velocity, and I direction x direction velocity, and we can divide it into the components, and then after that we can gather all these words, sum up, and then we can end up with the total momentum and impulse diagram or equation. In this example, 0.1 pound of golf ball is struck by the golf club, and travels along the trajectory shown. So here, right? And the distance is 500 feet, like it fly and then landed on this point, which is 500 feet differences. We don't know the initial velocity. We know the angle of the external force acting on this golf ball, and then the mass, which is m, is 0.1 pound, and r, the distance, is 500 feet. Okay, we know that the distance r is equal to this velocity, if we take the component, is gonna be v cosine 30 here, and in y direction v sine 30, right? If we take the component. So for the x direction, we are gonna have v0x, which is v cosine. So first of all, the initial velocity, if we have initial velocity at x direction, plus the vx, which is v cosine 30 multiplied by time of flight. R is 500, r v0x, the initial velocity is 0, so that means the t is equal to 500 over velocity cosine 30. Okay. The second thing is because we have 1 and 2 unknowns, but we have the one equation. We need another equation. We need to go through the y direction. So when we look at the y direction, how long is gonna be fly in the y direction, how high is gonna go, we are gonna say y, or the h, is equal to y0, which is the initial height, plus the vy, which is v sine 30, v yt, right? So it's gonna be how high, but it's gonna be acting the gravitational acceleration, which is 1 over 2 g t square. We need to write it. So what is the final height? Is again 0. What is the initial height? Is gonna be 0 plus y v sine 30, which is sine 30 is, we know that 1 over 2 is okay, then v over 2 plus or minus 1 over 2, g is 32.2 and t square. Okay, we have right now the second equation, which is constructed by v and t, and here is also v and t. So we have these two equations. When we subtract to each other, we can find the v, instead of t, we are gonna subtract here v, and we are gonna find v as 136.4 feet per second. So okay, we found the velocity, this velocity. Then we can find the force acting on it during the impulse. We know that from our equation, the mass multiplied by the initial velocity plus the impulse term, which is total of integral force, external force F dt, is equal to the mass, the final velocity. So we know that the initial velocity is gonna be, initial momentum is 0. Before impulse, before this force, is the ball is at rest, so there is no momentum. Due to the force, acting force, it start to activate and then give momentum. So F is not depends on time, it only depends on like how hard you struck, so that's why it's constant. So we can say F multiplied by the during time, it is 0.5 milliseconds, which is 10 to minus 3 seconds, right? is equal to the mass of this object is 0.1 is given pound, so we need to divide it 32.2 in order to get the slug. So 0.1 over 32.2 is giving us the mass, and the final velocity, which we already found here, 136.4 is our velocity, but we know that if we want to find the vectoral form, is gonna be cosine 30 in I direction and plus sine 30, because we divided into components, sine 30 in J direction. We find the magnitude, but we are gonna find the in vector form. So F, if we do these calculations, we can find F is equal to 735 I plus 424 J, and the unit of this force is gonna be pound. Alright, we solve this question and we find how much the external force acting on this ball and what is the velocity of this ball after this impulse. What about if we have a system which we have one system consists of many particles? Then we are gonna take all these terms into left hand side for the force diagram, and is equal to, we are gonna take this equation of motion. It's the same thing basically. We are gonna take into left hand side this dt term, and then we will just end up the total mass, each mass multiplied by the velocity, each velocity, and sum of all of it plus the impulse of this external force is equal to all these masses multiplied by the each velocities, the sum, the final velocity sum. We have the final equation of this momentum and impulse equation. This equation states that the initial linear momentum of the system plus the impulses of all the external forces acting on the system from time 1 to time 2 is equal to the system's final linear momentum. So as we say, this is system's initial momentum, the external forces impulse, and then final momentum. From our physics knowledge, we know that we can calculate it, the center of mass, which is m multiplied by the center of mass, the position, is equal to all positions, each distance to each particles. We know that the total mass is the total, each of these particles is equal to the total mass. And then we can similarly say that if we take both sides derivative with respect to time, is gonna give us the velocity at the center of mass is the momentum at center of mass is equal to all these each particles momentum additions. By using this one, we can simplify all this equation into m, the center of mass, this system's center of mass, initial momentum, plus all the external forces impulse is equal to the final, this system's center of mass final momentum. So we can simplify this equation. Instead of taking all these parts, we just simply go through the center of mass, and then we can find this system's momentum and impulse equation. What about the conservation of linear momentum for a system particles? When the sum of external impulses acting on a system of particles is zero, that means if there is no external forces acting on a system, that means we can take it out this integral f dt term, and the each mass multiplied by the each velocity, initial velocity, is equal to each mass multiplied by the the final velocity. So if we add each other, it's gonna be equal to each other. Then it can change into internal system path. This equation is referred to as the conservation of linear momentum. It states that the total linear momentum for a system of particles remains constant during the time period. So if we take mvg is equal to mivi, so it's gonna be, we can say that if we take the center of gravity, velocity, the initial velocity and the final velocity is gonna be the same if we take the center of gravity. If we take each velocities, it can change, of course, inside internal velocities with the particles. But as from here, as you can see, the center of gravity, not center of mass, center of gravity, the initial velocity and the final velocity is going to be the same. So the system velocity conserved itself. In this example, there are two rail cars approaching to each other, and the rail car A has 20 megagram of mass, and rail car B has 15 megagram of a mass, and velocities are A has 3 meter per second and the other one is 1.5 meter per second, and approaching to each other. The speed of the car A after collision, if the cars collide and rebound such that after collision B moves to the right side with a speed of 2 meters per second. So after the collision, the B is gonna go to the right side and is gonna go 2 meters per second. So we are gonna find A, if it is gonna go right or left, and how what is the magnitude. Also find the average impulse force between the cars if the collision takes into place, which is delta t is 0.5 second. Okay, we know that the total initial momentum is gonna be mi vi, which is v as a vector of quantity, is equal to the total final momentum, m, like this one mi1, this is mi vi2. Okay, when we write it down, we know that the A has 20,000 kilogram, which is 20 megagram, 20,000 kilogram multiplied by 3 meter per second, plus 15,000, which is B. We need to multiply 1.5 meter per second, but in left side, so let's put here minus, is equal to 20,000 multiplied by VA2, the final velocity, which we don't know and we are gonna determine, plus 15,000 multiplied by, in the right side, is going right side with 2 meters per second. Okay. Then after this calculation, we are gonna find the final velocity of A, the rail car A, is gonna be 0.375 meters per second. So it's plus, that means rail car A is also going to the right side, but instead of 3 meters per second, it's gonna go 0.375 meters per second. Alright. So we determine the velocity. After that, we are gonna use our impulse term. We are gonna say MA, and the mass of A, the initial velocity of A, plus the time duration from time 1 to time 2 f dt, which is impulse term, is equal to the final velocity of the rail car, the final momentum of rail car A. We know that MA is 20,000 kilogram. The first velocity is 3. We don't know this one, but we know that the force is constant. The average force is asking, so F average is constant. Let's write F average multiply by delta T, which is 0.5, and is gonna be equal to the 20,000, the mass of rail car A, multiplied by the second, the final velocity, which is 0.375. 375. And after calculation of these terms, because there is just one unknown, the average force acting during the collision is gonna be 105, about 105 kilonewton. Okay. So after this calculation, we find, like, after this, like, let's say they meet in this point, when they collide, the external force on each other is, external force acting on this body is 105 kilonewton from rail car B to on rail car A. Alright. Let's go through the impact term. Impact occurs when two bodies collide with each other during a very short period of time, causing relatively large impulse forces to be exerted between the bodies. So as an example, the striking of a hammer on a nail or a golf club on a ball. So like when you hit, there's a small time duration and there's a force acting on a body. So this is called the impact effect. We have, in general, there are two types of impact. One is central impact and the other one is oblique impact. Let's go through these two. Central impact occurs when the direction of motion of the mass centers of the two colliding particles is along a line passing through the mass centers of the particles, as is shown as this figure. The colliding particles is coming in a center of their mass centers to each other. Okay, so is in the line of impact, and when you see the center is colliding each other. So this line is called line of impact, which perpendicular to the plane of the contact. All right. So as I said, like the mass, the size of the balls may be different, but doesn't matter. The line of this center of mass is gonna be collide each other, like coincide each other. When the motion of one or both of the particles make an angle with the line of impact, the impact is said to be oblique impact. So as you see, it collide each other at a plane in the, let's say is a z direction is here, x direction is here, and when the, uh, the particles comes with an angle, so they are gonna go through, or it's gonna stick, and then it will move maybe in z direction, maybe like xz direction, or plus xz direction. So this is called oblique impact, and this is called central impact. In most problems, the initial velocities are known, and then we are gonna obtain the final velocities after the collision. In this regard, momentum for the system of particles is conserved, since during collision the internal impulses of deformation and restitution cancel. So that's why we are taking out the impulse term, and we know that each term's momentum, the initial momentum, is going to be equal to final momentum addition, right? So then, in order to obtain a second equation necessary to solve the final velocities of A and B particles, we must apply the principle of impulse and momentum to each particle. Then we are gonna say, okay, they have the first particle's initial momentum minus the impulse during this time period is equal to the final velocities of first particle, and similarly we are gonna do the second thing for the these impulse and momentum equations or other particles. After we have this 1, 2, and 3, these three equations, we need to define first these two impulses. This impulse is called restitution impulse. This one is restitution impulse, and this one is deformation impulse. And if we have the ratio, it's called E is equal to integral r dt over integral p dt, which is this E is called coefficient of restitution. And from this one, we know that we can take it into right side, and then we can put these guys into the left side, and we can see the velocity minus the final velocities of A over the first initial velocity minus the when the collision occurs velocity. When you take these terms, you will obtain the restitution of coefficient of restitution, which is the second velocity of particle B minus the first velocity particle A, the second velocity particle A, the initial velocities of particle A minus initial velocities of particle B. So this equation is important, and we will use this in our problems. In this question, the ball strikes the smooth wall with a velocity of 20 meters per second. The coefficient of restitution between the ball and the wall is 0.75. We need to find the velocity of the ball just after the impact. So VB2, we are gonna find it. With this kind of question, we need to pay attention that only collision is on the line of impact in y direction, or like let's say x direction. In y direction, it just smoothly goes through. So if we take into the components, we are gonna have in this direction, let's say Vx and Vy. Vy is gonna be same as before and after collision, because there is no effect on the y direction. Then let's write down our equation. So we can say m Vb1, the initial velocity of 1, multiplied by sine 30 is gonna give us the y direction. So sine 30 is gonna give this direction velocity is equal to m v the final velocity multiplied by sine theta, right? Because it's gonna be here. So this m is gone because it's the same, it's just one particle, and we know that the initial velocity of this guy is 20 meter per second with sine 30. Sine 30 is 1 over 2, so it's gonna be 10 here. 20 over 1 over 2, 20 multiplied by 1 over 2 is gonna be 10, and VB2 sine theta, which is, we don't know theta, we don't know VB, the final velocity of this particle. So we have two unknowns, but we have one equation. We cannot solve this equation. We need another one, which is in x direction. So right now we are gonna use coefficient of restitution term, which is E is equal to the final wall velocity, right? So the one particle is this one, the other particle is the wall. What is the final wall velocity? Is 0. The wall is constant, it doesn't move anywhere, so it's gonna be 0 minus the balls, I mean these particles final velocities in x direction, but VB2, but instead of sine theta right now we are gonna use cosine theta over, right now VB1 multiplied by VB1 is 20 meter per second, right? Multiplied by cosine 30 minus the wall initial velocity, which is again 0. So we can find it. We know that coefficient of restitution is also 0.75. So we have again two unknowns, which is theta and VB2. So let's write it down. VB2 cosine theta is, if we take these guys into the right side and then multiply, we are gonna have 12.99 meter per second. So we have here our second equation. The first equation, we have VB2 sine theta. Here we have VB2 cosine theta. If we divided each other, we will have, like, let's do this one, VB2 sine theta is equal to 10, and let's divide it. VB2 cosine theta is equal to, let's divide it here, 12.99. So we know that this guy is gone. Sine theta cosine theta is tangent theta. Tangent theta is gonna be 10 over 12.99. Then 12.99, let's say 13. Arctangent for both sides is gonna give us theta is equal to 37.6 degree. 37.6 degree. After you find theta, you just plug any of the equation, then you will find the final velocity of this particle as 16.4 meter per second. So we find the final velocity of this particle and the angle after the collision. In this question, a girl throws the ball with a velocity of 8 feet per second in the x direction. The coefficient of restitution between the ball and the hard ground is 0.8. We are going to find the rebounding velocity of the ball and the maximum height of h after the rebounding. Okay, so we know that in x direction there is no effect cutting the velocity after the collision. So v1 x is going to be equal to v2 x, which is the after collision. Both of them is 8 feet per second. Only difference is in y direction because it's hit and rebounding. How much the velocity when it lands here? We will need to do the free fall because at the here there is no y velocity. Let's find it down as our final velocity square is gonna be equal to initial velocity square. Initial velocity square minus 2g and delta y, which is, we know that initial velocity is 0, this guy is gone 0, and we know that the velocity square is gonna be equal to minus 32.2, and delta y is gonna be minus 3. If we don't plug minus 3 here, it's gonna be imaginary because we need to take it out this minus. Then we can find velocity is gonna be equal to square root of 6 multiplied by 32.2. Then, like when we make the calculation, we are gonna find 13.9 feet per second is gonna be our final velocity in y, vy2. Okay, so no, vy1 before the collision, when it hits here from this height to the down, is gonna be 13.9 feet per second, from 0 to 13.9 feet per second velocity gains due to the potential energy. Then it rebounds. We will use coefficient of restitution. The hard ground's final velocity, the ground is constant, is gonna be stuck there, so it's gonna be 0 minus the ball's second velocity, which is, we don't know in y direction, of course, vy2 over the first velocity of y, which is 13.9, minus the ground's second velocity, which is 0, is equal to 0.8. So which means we can define from here vy2 is gonna be 11.12 feet per second. It's gonna be come out here minus because we didn't plug here. Let's plug here. It's gonna be minus direction because it's gonna be minus direction downward. So it's gonna be this one. It's gonna be plus. So the after collision we see the second velocity of in y direction component is 11.12 feet per second. So the final velocity of this ball in vectoral quantity is 8I plus 11.12J. So this is our final velocity of the ball. And how high is gonna go after the collision? We can use the same formula as v square is equal to v0 square minus 2g delta y, which is here delta y is h. So v square, the final velocity is gonna be the maximum point is gonna be 0, so this guy is gonna be 0, and v 0 is equal to v0, the initial velocity in y direction, of course. Y direction initial velocity is 11.12. So I will write it down. 0 is equal to 11.12 square minus 232.2 h. So if you do this calculation, you will find h as 1.92 feet. So after the collision, like rebounding from A, the ball is gonna go 1.92 height. First we drop, like the girl drop, basically the girl drop from 3 feet high. It bounces from the hard surface, which is the coefficient of restitution is 0.8. Then it loses its momentum, and then it goes till 1.92, and it starts to bounce again and bounce again till the height is gonna be 0. Alright, this question is done.